All right. Yeah. So, welcome to the lecture number 3 of our course on quantum photonics. And today, finally, we're going to discuss some aspects of transitions and atoms, and we'll finalize the lecture with the Purcell effect. Yeah. So let us quickly recap what we've discussed last time. Right. Last time we focused on the key points of quantum quantum mechanics and quantum physics. We started with introduction of the Hilbert space. We said that Hilbert space is a arbitrary dimension, complex valued vector space with well-defined distance between 2 points or 2 vectors. That allows us to introduce the concepts of probability amplitudes and describe any state of a quantum system as a vector in the space. Okay, and so since we are talking about vectors, describe quantum states by vectors, we introduce a new notation for the vectors. It's called bracket notation. So bra vector is a raw vector of the elements, and the number of elements is equal to the dimensionality of the Hilbert space. Ket vector is a column vector. These two vectors can represent basically the same state. Let's say you have a state A, like this row. You can write down exactly the same ket vector with complex conjugated amplitudes, coefficients of this vector. And these two vectors, they called dual. They represent the same state and just connected through complex conjugation. In general, this state vector can be arbitrary, and we can decompose this state vector by its projection on the basis vectors. The basis vectors in this bracket notation we denote like 0, 1, and so on, up to n. N is the dimensionality of this space. It's just like any decomposition of any vector in our ordinary space, three-dimensional Euclidean space. This is also decomposition of a complex valued vector in the Hilbert space by the basis vectors 0, 1, and so on. However, very important point to mention here is that these projection coefficients C0, C1, and so on, they are complex valued. And that's the key aspect of quantum mechanics. Okay, without using complex numbers, it's not possible to introduce quantum mechanics in a rigorous way. And that's interesting because this complex valued complex function area of math is like traditionally introduced like a auxiliary math technique or approach to solve some problems rather than like real numbers. But without these complex numbers, it's not possible to develop quantum mechanics. It's just like positive and negative numbers in electrodynamics, right? We in our real life, we also don't encounter negative numbers often. In fact, one cannot provide an example of a negative number in just nature, right? These negative numbers have been introduced when people developed trading, right? When you have like negative balance, you owe some money and so on. And after that, having these negative numbers, it allowed us to introduce electrodynamics, because electrodynamics is all about positive and negative numbers. Yeah, so something similar happened here. New math led to a new physics. The next point we discussed last time was about projective measurements. So our system is represented by a vector in a Hilbert space. What happens to this vector when we measure system? The vector collapses to one of the basis vectors. Okay, one of these basis vectors, 0, 1, and so on. So it basically became parallel to one of these basis vectors. And which vector, we don't know which one. It's totally arbitrary, probabilistic. We just can say the probability of getting this or that final result, and this probability is given by the absolute value of the projection coefficient, the corresponding projection coefficient. And of course, the sum up of all the absolute values squared of this projection coefficient must be add to 1, because the probability of getting any result is 100%. Qubit is a system, is a simplest possible quantum system. It's just a system with two possible quantum states, two possible basis vectors, and the corresponding Hilbert space is two-dimensional. And when we measure qubit, we get either one, either state 0 or 1 with the corresponding probability C sub 0, C sub 1. Then we say that, okay, we have the state, different things can happen to the system. We need to describe the evolution of the system over time and space, of course. And how we do so? We do that using the Schrödinger equation approach. This is one of the most fundamental equations in physics and nature. In this equation, you can notice immediately I, right? So it's an imaginary unit there. If you like forgot to write this I here, right before the time derivative, it wouldn't work. Okay, one of the most fundamental solutions to the equation like this is the harmonic oscillation, like harmonic oscillator solution with sinusoidal or sinusoidal solutions, and that's all possible only if you have this I in here. Yeah, so it's a time derivative equation that allows you to find the psi function, sub psi vector in the next time instant. Particularly important case when this H, this Hamilton, doesn't depend on time. We call these solutions stationary solutions. And the solution, of course, depends on time through this exponential factor in here. But the amplitude doesn't change in time. And since the probability of finding the system in this or that point in space, place, doesn't depend on time. Okay. Using this approach of the stationary solutions, we discussed the particularly important case of the hydrogen atom, right? We say that the energy levels are numbered by this main quantum number n, so 1, 2, 3, and so on, theoretically up to infinity. And at every single n, which defines energy, we also have two other quantum numbers, L and M. So L stands for the mechanical orbital momentum, right? So this number describes the value, the magnitude of the mechanical momentum, basically the way how these electrons move around, spin, or orbit around the nuclei. And M corresponds to the orientation of this momentum in space, in simple words. Also, people observed the fact that electrons, as well as nuclei, protons, neutrons, they have spin, which is the inner mechanical momentum, which has no like classical analogy. It's purely quantum characteristics, and this inner momentum can get just two orientations in space. When we try to detect it, we can find either plus, like either up or down direction of the spin. And no other solutions are there. And finally, we discussed the concept of harmonic oscillator, right? Harmonic oscillator is a system that is described by quadratic potential function. Like, for example, in real life and mechanics, we have this pendulum. This pendulum swings in gravity field, and this is described by the potential function, which is proportional to the coordinate square, or the mass on the spring. It's also defined by k times this deformation squared over 2, this potential energy. So whenever you have this situation of the parabolic potential, you can apply the concept of harmonic oscillator. And this is one of the most important concepts in physics. In fact, all today's modern theories like quantum electrodynamics, quantum like gravity, many things, quantum optics, photonics, of course, we often describe things in terms of harmonic oscillators. Yes, that's what we discussed last time, and we of course discussed this harmonic, the hydrogen atom and its orbitals and states. I just want to briefly recap it here again to be on the same page, because it's important for what I'm gonna discuss today. So let us once again look at this nice electron shell sketch of a hydrogen atom, right? So we have one proton in the center, one electron that orbits around the nuclei, and the electron can transit, can be at any these orbitals. It's not orbitals, the shells, the state, energy states, defined by the main quantum number n. And for every shell n, we have different electronic configurations described by subshells, right? And these subshells, they consist of different orbitals. So these circles, these points, these circles, red, pinkish, blue, green, they describe they represent the orbitals. right? Different electronic configurations. So, for example, for the main number 1, we have one orbital 1s, where s corresponds to the L number equals to 0, right? Again, if we have n equals to 1, then L can be only 0, and M can be only 0 too. So that's why we have only one orbital. For the n2, we have two possibilities, because if n equals to 2, L can be equal to 0 or 1, and M can be -1, 0, 1, and also 0 again, right? So that's why we have one orbital here at the shell 2s, and 3 orbitals on the shell 2p, and so on. And let us consider the third case, the state number 3, right? So for the state number 3, we can have L to be equal to 0, 1, or 2. So 3 different magnitudes or electronic orbitals with 3 different magnitudes of the angular momentum. We denote them by S, P, and D. So that's why we have the orbital S, group of orbitals P, group of orbitals D. And each group, they can have different number of configurations. That's defined by the orientation of this momentum, angular momentum in space, defined by number m. Right. That's why for this configuration 3s, we have 0, we have just one orbital. For p, we have 3 orbitals. For d, we have 5 orbitals, and then so on. Yeah, just as I said, L defines magnitude of the orbital magnetic moment. Magnetic and mechanical, angular mechanical momentum, and M corresponds to the orientation of this momentum in space. Mechanical momentum and magnetic momentum are similar here, because what causes the electron move around the nuclei, you can consider this as a loop of current. This loop of current represents the magnetic moment, as we discussed probably on the first lecture. A loop of current represents magnetic moment, and that's why this L number also defines the magnetic moment of the orbital. Okay. Yeah, maybe about this one. So when you look at the pictures like this, these are the energy levels of the hydrogen atom, and typically they start from something like minus 13.6. So what does it mean, this minus, this negative energy? Well, in this case, in the case of bounded states, okay, so it's not free state, it's bound to some area in space, like in atom. Atom is the bound configuration of electrons and protons, neutrons. In this case, we count energy from 0 and from the 0 level, and everything that goes down is negative, is a bound state. All energy that is positive, like kinetic energy, you get an electron from the atom and it gets some kinetic energy, so it will be, that energy will be positive. That's why this energy level is negative. Yeah, we say that last time, we say that not all these energy levels or orbitals can be excited optically because of the selection rules, right? So last time we said that, so first of all, we need to match the energy. So the energy conservation law applies here as well. The energy difference between final and excited state must be equal to the energy of the photon that comes to the atom. And also the type of polarization by which the atom is excited, or the polarization of light that is emitted from, radiated from the atom, is defined by the quantum numbers L and M. Okay, so for example, for all transitions where we have no change in M, but for example, only L changes, for this type of transition, we get linear polarization. Or this type of transition can be excited by light with linear polarization, just like a laser in the lab when you did the lab work. So that laser gets one vertical polarization. Other types of polarization allowed, for example, this perfect circular polarization, either clockwise or counterclockwise, or right-handedness, left-handed polarization. So this type of wave is radiated, emitted by transitions with the change in M. Okay, so if M changes, then we can get the circular polarization. Today we're gonna talk much more about these transitions and what kind of transitions can result in different types of light. And speaking about these effects, we need to introduce the concept of electric dipole and the elementary electric dipole and magnetic dipole. Okay, so electric dipole, you know, is a structure like this. It oscillates like a positive and negative charge oscillating in time like this. And if you look at this picture from the larger perspective, you will see how it radiates electromagnetic fields. So any oscillating current or oscillating charge radiates electromagnetic field. And we describe this system, this characteristic, by electric dipole moment, right? This vector mu here is electric dipole moment, is equal to minus E, which is elementary charge, times R, which is the radius vector of either charge or the distance between the charges, depending on the coordinate system. Important point to notice here is that this R, so the configuration of this dipole moment is totally defined by R itself. And this R is a odd function, right? You know this concept of parity. The function can be either even or odd, or neither one. So this function is odd, meaning that if you flip the coordinate system, if you replace all coordinates by minus, the R becomes minus R, right? And so you get this minus in there. And so this is the odd function. That's important because if we're talking about magnetic dipole, which is again represented by a loop of current, like elementary, sometimes people say ampere loop of current, this function, this quantity is represented by R cross product, outer product with the current. Right? So it's an outer product. And if you do the space inversion, again, all the coordinates get minus. Now this R gets minus, the current gets minus, so you get minus and minus, and they cancel each other. So this magnetic dipole is even function of the coordinate. Okay. Why that's important? It's important because we quite often we need to calculate the integral like this one here. So like some one function, then some other function, and then the integral of two. And if you consider the integral of two, let's say two even and odd functions. Integral of two functions, one is even, another one is odd. If you take the integral of these two, you will get 0. That's easy to understand because if you integrate over the entire space, I just don't know how to pause this animation here. Anyway, so one part, because of the parity, one function is even, another one is odd. So at one part you get positive contribution, but when you go across the 0, across the origin coordinate of the coordinate system, you get one function, even function stays the same, but odd flips the sign. So like in totally integral, the integral vanishes. You get 0. And so let us, and quite often, like usually, the parity of a quantum system is defined by this quantum number L. Okay, the L defines parity, meaning that the quantum states of different L, they are different in parity. So for example, let us consider this integral here. And let's suppose that they have the same parity, this psi2, psi1. They have the same parity. And by the way, this integral represents the dipole moment in quantum. So you see this minus E and then the matrix element of R. Okay, so this integral here is nothing but the mean value of R. So you take this integral, you assume first that these two psi functions, they have the same parity. So let's say even functions. Then this function is even, this one is even, but if you multiply by x or r, which is odd, this second part becomes odd. And in total, you get the product of two even and odd functions. So this integral vanishes. So we conclude that for the electric dipole transitions, the electric dipole transitions allowed only between states with different opposite parity. Okay, so that's why usually, typically, these electric dipole transitions happen between states with different L. For example, between L 0 and 1, or 1 and 2, or 0 and 2, and so on. So this L must be different for the electric dipole transition. And in drastic contrast to magnetic dipole transition, which is, as we said, it's a even function, and hence the matrix, the corresponding matrix of the magnetic dipole transition vanishes for the functions with opposite parity. So the parity of the psi function must be the same for magnetic dipole transitions. Yeah, so in here, let me see. Yeah, I'm confused. This real with ideal or perfect hydrogen atom. Okay, so it's let me see, I lost the logic. Yeah, so here we discuss the perfect hydrogen atom, right? So this is the perfect case. There are some effects that we don't discuss yet, which change the picture, this perfect or ideal picture. And the first effect here is to acknowledge is so-called fine structure or fine fine splitting. So what is fine splitting? So we said that in a hydrogen atom, right, we have this nuclei and circling, orbiting around the electron, and the electron gets magnetic momentum, right, magnetic moment defined by L. And the electron itself, it gets spin, right? So the spin is inner magnetic momentum. It's like a small magnet. And this orbital, if L is not equal to 0, if L is not 0, then this orbital also gets magnetic moment. So effectively, you get two magnetic moments, one coming from the orbital and another one coming from the spin. And these two magnets, they of course can interact. They can align either against to each other or in parallel, right? And these two configurations, they have different energy. Like if you ever played around with magnets, you can arrange two magnets like this in parallel. But if you just a little bit change this configuration, it can be stable. But if you just a little change it, it will like transit to the opposite state. Something similar happens here. So we, instead of just one upper state to P, we get the splitting of the two states. And we call this splitting like fine structure or fine splitting. Why S state configuration doesn't split? Because S configuration gets L equal to 0. So no magnetic moment, no orbital magnetic moment, but the electron, of course, gets the spin, but this spin doesn't interact with zero magnetic orbital magnetic moment. So since now we're talking about two moments, one is orbital, another one is spin, we need to bring another quantum number to the picture. It's called J. So this J number is just the sum plus minus mechanical and spin. So the notation like this 2 pi 3 half, right? So this 2 pi 2p corresponds to the main quantum number 2, L equals to 1, and this 3 half is simply 1 plus 1 half, this orbital momentum 1 plus 1 half from the spin. And similarly, the second state gets this index 1/2, which is 1 minus 1 minus p. So this is the way we denote these states. Okay. Also, this splitting can be changed. The amount we split these two levels, we can be changed by placing the atom in a magnetic field, because the magnetic field the spin interacts with can come not only from the orbit but also from the external source of the magnetic field, and we can vary this splitting, and that's important for many applications actually. Yeah, so let us look at this real picture of the hydrogen atom, and let's recognize now that we have different transitions now, right? So we can have the transition from either 2p 3/2 to the state 1s, or 2p 1/2 to the state 1s, or transition between these two p states. Okay, so all these states are possible, but with different probability, different energy, and so on. The characteristics of these transitions will be different. And let us consider, for example, transition 2p 1/2 to the state 1s, right? So different p, the different letter means different L. So this transition is allowed in the electric dipole regime, right? So the photon, so this state, this transition is allowed and can be bright in the experiment. Right. Also, there is no this transition can happen or can be excited by the linearly polarized light, because it can happen with or without change in magnetic number m. Right. And secondly, this transition, yes, and by the way, I also forgot to mention that this level 2p is not just 2p, right? It's two levels there, 2s and 2p, because in the perfect case, I remind you that we have these two orbitals, two subshells, 2s and 2p. This s here, 2s, also doesn't change, doesn't get this fine structure because L is equal to 0. But the allowed state is there, and this state can also interact with other states and lead to different types of transitions. Right. So we also have these possible transitions from 2s to 1s. So from this 2s to 1s state, it's possible, but the fact that this letter doesn't change means that the L doesn't change, which means that this transition is not allowed in the electric dipole regime, but totally allowed in the magnetic dipole regime. So this transition is called, or can be considered as, a magnetic dipole. In fact, these magnetic dipole transitions, they are much weaker, much less probable in nature because of the because of the nature of any magnetic effects. They are intrinsically weak. So these two transitions will be very weak, and we probably won't see them in experiment, but these two transitions will be very bright. All right. But that's not the end of the story, right? So this real hydrogen atom also affected to another effect, which is called hyperfine structure, hyperfine splitting. what it is? It's about the fact that not only electron gets magnetic moment, but also the nuclei can have magnetic moment if the number of protons and neutrons in the nuclei is odd, then the nuclei can have the resulting magnetic moment. And now again we have the case of two magnets, right? One from nuclei, another one from the electron, and then they can again align either coincide or oppositely oriented. And these two configurations have different energy, and as a result, we get this hyperfine splitting of all states, including state 1s. I remind you that for this effect, state 1s didn't change because this L is equal to 0. However, now even this state 1s can split because of the nuclei electron spin interaction. Okay, so hyperfine structure. So as a result, this is the structure we discussed, we call perfect, right? 1s state, then the state that composed of two shells, 2s and 2p, and then and so on. If we turn on the fine splitting, we get the structure like this, right? So it's already 4 states. And of course, always we have this hyperfine splitting too, which results in how many? Eight energy states. So everything is splitted. Everything is splitted. And so this transition between two hyperfine states in 1s is very important. For example, astronomers, people who study space, nature, they using this transition, detecting the radiation that comes to Earth from space that corresponds to this frequency transition between these two states. Analyzing this data, this signal, you can tell how much hydrogen we have in space, in cosmos. Okay, so that's something very important and allows us to investigate something that is very, very far from us. So atoms can radiate different frequencies, different light, right? What typically happens next is we make this light of different wavelengths, of different frequency pass through something dispersive. And this dispersive can be, for example, this prism, right? So at the first lecture, we discussed that any material, actually, it gets the frequency dispersion. It means that different wavelengths or different frequency or different color, you name it, the light propagates with slightly different frequency. Okay, and you can use this effect to turn the signal, the light, into the spectrum. Okay, so you can get the spectrum from the light. It works just like the spectrometer you saw in the lab. You remember when we measured the spectrum of the light source. The light source, of course, emits light. You can notice the color and so on, but you cannot tell what the frequency composition of this light. But you can use this spectrometer to turn the spectrum into the this number of lines. And this is how it looks like for some gases. For example, this hydrogen creates the lines like this. Helium creates other lines. Argon, nitrogen, neon, mercury, carbon monoxide, and so on. All these gases have a unique spectrum. You can say like a gas fingerprint, right? It's very, very unique. Using this approach, for example, like measuring the light that comes from the sun and making this spectrum, we can exactly say what gases the sun is composed of and how much hydrogen versus helium, for example, in the sun. And we know this, we have these theoretical models how the sun burns, right? How it lives, and we can tell like the age of the sun. We can tell like when it will burn down the energy, and so on. So we can tell many things. Also, measuring light from like very distant stars, like stars we never reach to because they're so far from us. We can tell what their atmosphere, not only stars but also the planets, right? We can tell what their atmosphere is composed of: hydrogen, helium, and so on and so forth. We can tell if the planet gets the water in atmosphere and so on. So it's very important approach, and it's important to understand how all these things work. And of course, the bottom line is that the atom gets energy transitions. We can excite these energy transitions, and the atom can re-emit light back because of this spontaneous down transition from excited state to the lower final state. It depends on many factors, and one of the main factor is the factor of temperature. So for example, here, this picture, you can see a spectrum, just like the one we got in the lab, as a function of wavelengths, intensity here. And so the room temperature, this red curve, you see it's wide, it's broad. But as we cool down the system, for example, up to 77 Kelvin, so it's already very cold, you see how this emission line gets narrower and appears like a spike in there. So temperature is very crucial parameter because, of course, we have many levels: fine structure, super fine structure, hyperfine structure, and so on. And temperature allows these all transitions, makes this all transition contribute to the final result of the photoluminescence. Okay, so photoluminescence is light that comes from the material if we excited by light. So photoluminescence or fluorescence. And if you need to locate just one transition, we need to cool the system down to low temperatures, typically. With maybe some few examples of atoms like hydrogen, when these energy states are so rare, they are so they located so far away, so we can induce just one transition. Other materials, look at argon, for example, or nitrogen, right? You see how many lines are there, and of course they are interfere when the temperature is not small. We describe the shape of these lines by the function that's called spectral line shape function. I refer to the Fox book here. I encourage you to read the chapter about photoluminescence. Let me instead, I have maybe just 10 minutes. Let me instead tell you about the damping and T1, T2 times, okay? Because they are very important for quantum across the disciplines, from quantum computing to quantum photonics. So what is T1, this time 1? So if you consider some sort of an oscillator, it can be, for example, electromagnetic resonator, like demonstrated here. So this ball represents a resonator with a trapped electric field there. Okay, and of course, if you will observe this field in the resonator for a while, you will notice that the field there decays, right? And if the resonator gets just one mode, this decay will be more or less exponential. And this T1, it represents the time when of this mode decay by a factor of E, right? 2.7 times for the energy of the of the field. So it's called decay time. The process is decay of energy because we observe how the energy decays in the resonator. Or if you have the pendulum, for example, you observe how this amplitude of the pendulum gets smaller and smaller and smaller. Again, this is the effect of decay. There is another effect possible here, usually caused by some noise effect. For example, our cavity, our resonator can be made of some metals. Metals are conductive, and conductance means some noise. It's called Nyquist noise. Something noisy happens here, and noise means that if at the initial time moment T1, I have very well-defined direction of this polarization of the field, for example. Let's say it oscillates up and down like this. In the next time moment, in a while, let's say T2, we will observe that this field oscillating not just up and down, but also can oscillate slightly inclined, right? Not in just one direction, but it can get different directions spontaneously. And in another time moment, T3, we can observe that the field totally oscillates totally in an unpredictable way, like totally chaotic, right? So it's an unpredictable state. So the energy is there, the mode is there. It just oscillates in a way we don't predict it. It's kind of a noise. We say that the field lost its phase. So it's the field state is dephased. Yeah, and that's why this process is called dephasing. And the time, characteristic time of losing the state, it's well-defined state, right? The mode loses its state. It's called T2. So it's a dephasing time. Just like in quantum, if we consider our atom or a qubit, whatever, with two states, 1 and 0, ground and excited, different dissipation mechanisms, like temperature, like losses, and so on, they lead to decay. Decay means we excited our atom to the excited state. In a while, the atom transits back or dissipates its energy through some heat and so on. So it's decay. Dephasing is another mechanism when, for example, we have heat, like our temperature is like we observe atom at room temperature. Because of this room temperature fluctuations, the ground state and the upper state, they fluctuate. And so the atom loses its phase. Okay, so the atom is dephased. And this dephasing is a main mechanism of broadening the emission line here. So this emission line here is so broad because of these thermal fluctuations. If we cool the system down to, let's say, 70 Kelvin, we observe how these fluctuations slow down and became more stable. So the atom doesn't or lose its phase much slower, and this T2 time is increased. This interaction of the atom with different systems can be used in a very interesting way. And before talking about that, let me show you maybe one video. So do you see my YouTube
Yes.
screen? I'm gonna turn it on. Let me know if you don't hear it, okay?
Okay.
Did you hear anything?
No.
Then let me try to turn it on. It can take a few moments. Let me see. More. Yeah, share computer sound stereo.
Primitive and simple. How it works.
Oh, we
Do
can
you hear that?
Yeah.
You can?
Yes.
Okay. So let us watch this part here. So it's totally about acoustics, not optics, okay? But the same principles hold in optics too. So let us watch this one first.
To tell you when it's in tune. So it's very kind of primitive and simple. How it works, we simply just give it a whack. So you just kind of hit it. Usually if I'm sitting down or even standing up, I'll hit it on my knee. You know, I'll bring my knee up and do that if there's nothing else around. And that's sufficient. You can hear it creating that nice A note. But I'll just bang it on the table here or my chair.
So you see what happened. the guy gets the tuning fork. It's called camber tone sometimes. So this thing that you use to fine tune the musical instruments. Okay, and he first excites this fork, so it starts like oscillate. It vibrates, but the sound from this fork is very weak. You barely can hear it. Okay, but when the guy brings this fork to the guitar resonator, the fork starts sound much more intensely. Let us watch this one again.
Usually if I'm sitting down or even standing up, I'll hit it on my knee. I'll bring my knee up and do that if there's nothing else around. And that
so you hear almost no sound. And what happens next?
Sufficient. You can hear it creating that nice A note.
So you see how how strongly this fork starts sound. So that happened because you have something that radiates. In this case, it's a radiation of sound, like acoustical waves, the oscillation of the pressure, for example, in the air. And initially, this fork is small, meaning that it doesn't radiate much, so the source is poor. But if you couple this fork to a resonator, a system that is tuned to the frequency of this fork, because of the interaction of the fork with the resonator, the fork starts radiate much more intensively. So here is the question. So we hear much stronger sound. That means that the energy of this wave is much more intensive, right? The intensity is much larger. So what happens to the energy conservation law? What do you think? If the fork radiates more, it radiates more energy. Where this energy comes from? So the energy comes from the fork itself, of course. So the point is that the fork, it starts radiating more, but this radiation happens faster. Like the fork radiates much faster with the resonator than without it. And we use this effect for many things. And in electromagnetics, in quantum, in optics, this effect is called Purcell effect. The Purcell effect consists in the effect of boosting like light emission or electromagnetic emission from a source coupled to a resonator. Like if you want to make our light source brighter, we can couple it to a resonator. Of course, it doesn't generate new energy. The resonator, it just makes the atom radiate faster. So per 1 second, the atom radiates like more photons. Okay, that's why we see it's brighter. It just decays much faster. This is what happens. This is a typical experimental result, like normalized photoluminescence as a function of time in nanoseconds. Okay, and for example, in a case without resonator, it's called substrate, the atoms radiate like this in time. Okay, so it's a exponential process. This axis, this y-axis in logarithmic scale. So this linear means exponential decay. And if we couple the atoms to the resonator, in this case, it was some sort of antenna. Antenna is another type of resonant structure. The atoms decay much faster, like, I don't know, like 100 times faster. And that means that per second, the atoms will radiate more energy, and the atoms will become brighter. And this is what happens in the frequency domain. Okay, so again, if you take the slide, use the spectrometer to decompose it into the wavelengths, spectrum. This is what we get. This weak line corresponds to the free space, no resonator, and this strongly enhanced signal corresponds to the to the resonator case. It is not just about enhancement. So sometimes we need to enhance some process, and we tune the resonator to boost this light emission or acoustical emission, and so on. Sometimes we need to suppress some effects. That happens often in acoustics. Like, we can tune this resonator to destructively interfere with the fork. For example, this fork in guitar and fork, we can actually make this fork sound even weaker by placing this, coupling this fork into the resonator, which is out of frequency with the fork sound. So if no mode, if no resonance in the resonator at the frequency of emission of this fork, of the source, there would be no energy radiation, and the fork would oscillate much longer. One interesting effect here is what people call muffler in car. So again, let me know if you can. I can actually check that. How do I check that? I forgot. Anyway,
it's just like the waves you
did you hear that?
Yes.
see when you throw a stone into the water. If you throw two stones at the same time, the waves interfere with each other. That's exactly what's happening with sound waves. Sometimes you get constructive interference, which happens when the waves combine together to create a larger wave. This results in a louder sound. But sometimes the waves are out of sync or phase and they cancel each other out. This is called destructive interference, and it reduces or cancels the sound. The muffler reduces the engine noise by reflecting the sound waves in such a way that they cancel each other out. In addition to the inner workings of the muffler, it's also constructed from layers of metal that help absorb the sound. The muffler quiets the engine, but it doesn't deal with the fume problems. So Milton begins working on making improvements to the engine. He looks at cooling and having the intake and outlet manifold on opposite sides.
Yeah, so you hear that. Imagine, right, the exhausting system of a car without this muffler, it sounds very noisy, very loud. And the way we cancel this noise, this sound, is using a resonator again, just like here for atom. But we designed this resonator in a way that the partial waves cancel each other. Canceling each other means that no resonator mode in there to couple to, basically. And since if no mode, we suppress the sound. So this is another kind of application of the same effect. So it's very general effect, this Purcell effect. You can encounter it in quantum, optics, photonics, in electromagnetism, in acoustics, in water waves, and so on and so forth. And understanding of these concepts is like kind of key for all this. The only difference is that in optics, these resonators, they must be like small. Sometimes these resonators are just small pieces of metals, metallic nanoparticles, or dielectric nanoparticles. So Lara, if you're doing this research on these nanoparticles, this is exactly what I'm talking about here. All right, so thank you very much, and let me stop the recording.